Okay, thank you. So let me begin by summarizing what we have learned yesterday. So we took a pair of punctures, take a pair of punctures, with local coordinates W and W prime. And then we sort them together using W prime equal to minus Q. Okay. And these pair of punctures could either be on the same Riemann surface or different Riemann surface. Doesn't matter. Same or so this produces a new surface. So this gives a new surface. On the other hand, for correlation function, this is achieved by inserting a certain quantity okay, inserting the following object. We had phi s of 0. I wrote the R first, phi r of 0, phi s of 0, then phi rc, phi sc, and then minus q to the hs, q bar to the hs bar. Okay, where hs and hs bar are the L0 are the conformal weights of phi s. Okay, which is the same as the conformal weight of phi sc or phi rc. And these, even though I've written both as 0, okay, so these are used, inserted using the corresponding local coordinate system. So this is in W coordinates, and this is in W prime coordinate. Okay, so they are not really at the same position. It's just that in the W coordinate, it's at W equal to 0. In W prime coordinate, this is at W prime equal to 0. So this relates the correlation function on the new Riemann surface to the correlation function on the original Riemann surfaces. Okay. And then we said that using this repeated application of this application can give the correlation function on any Riemann surface. Okay, because the higher genus Riemann surface you can build by sewing together handles on sewing together punctures on a sphere. Okay, if you take a sphere and you sew together n pairs of punctures, you basically add n handles. Okay, so this becomes a genus n Riemann surface. Okay. So this is an in principle construction. In practice, when you actually want to calculate the correlation function on the Riemann surface, there are other tricks. In practice, one can combine this with analyticity, okay, because there are various holomorphic fields, and operator expansion to find closed form expression. But the point is that in principle, you can just use the sewing procedure to build up all the correlation functions. Okay. And this also says something else, that all correlators are obtained from knowledge of conformal weights and sphere 3-point function. Because you can start with sphere 3-point function and then start showing punctures to build spheres with a larger number of punctures, and then you can start showing punctures on the same sphere to build up the higher genus correlation functions. Okay. The conformal weights are needed because, as you can see in the formula that we had, okay, you do need the information about the conformal weights of the basis states. So this procedure is called plumbing fixture. The procedure of sewing that he described it's often referred to as the plumbing fixture. Where it's like connecting the two punctures by a pipe. Okay, you are just adding a handle. Now we have to check for consistency. Okay, so let me explain where the consistency requirements come from. That often what happens is the same Riemann surface with punctures may be built from sphere 3-point function in more than one weights. So I'll just give an example. Okay. Take, for example, a sphere with 4 punctures. Okay, so you have 4 punctures, 1, 2, 3, 4. Okay. And suppose you want to build this out of sewing a sphere, 2 spheres with 3 punctures each. Okay. Now this we can do in 2 different ways. Okay, you can see easily. One is that you can cut open a circle here. Okay, think of this as the third puncture. Okay, so you are showing a sphere with 1, 2, and a puncture that will be sewed, and 3, 4, and a puncture that will be sewed. So that this is that. So you can build the 4-point function that way. Okay. Or you can cut open here and sew together a sphere with 2, 4, and a puncture, and 1, 3, and a puncture. Okay. And the question is, do these give the same answer? Similarly, for a torus 1-point function, okay, that's another example. Take a 1-point function on the torus. Okay. And you can ask, how can we think of this as a sphere with, so you can clearly see that a torus 1-point function you can get from starting with a sphere 3-point function and then showing 2 of the punctures of the sphere by hand, by this plumbing fixture. Okay. But again, this can be opened up in 2 different ways. Okay. We can either cut open this circle Okay, so it should be clear what it means, that you are just joining together like this. The other way is perhaps not so visible from the diagram, okay, but the other way is that you can cut open along a circle like this. Okay. Now, even though it doesn't look like a plumbing fixture of a sphere, you can easily convince yourself that it is. Okay. And the simplest way to convince yourself is that there is a symmetry on the torus that exchanges the two cycles. Okay, so if this is one way of getting the torus, this should also be another way of getting the torus. Okay. And again, the question is, do these different ways give the same answer? Okay. So this, in fact, okay, this consistency, okay, is part of the consistency requirement of CFT. Okay, so if this fails, if these two procedures don't give the same answer, okay, then we declare that the underlying CFT is not a consistent CFT. Okay. So this is known as crossing symmetry. This is known as modular invariance. Okay, these are just names for these consistency checks. Okay. So it's clear that in principle, there are infinite number of such consistency checks. Because given a higher genus surface, you can cut open in so many ways. Okay, and each of those should give the same answer. So there are infinite number of consistency checks. Okay, so this would seem to imply there are the infinite number of constraints. So number of constraints is infinite. Fortunately, there is a very useful result, okay, which says that as long as sphere 4-point function and torus 1-point function are consistent, all higher genus correlation functions are also consistent. So you don't really need to check infinite number of constraints. Okay, all you have to do is to check that the theory has crossing symmetry and modular invariance. Okay, now let me give an example, an exercise. So exercise, prove that on a genus G Riemann surface, we need total host number minus 6G minus 6 to get a non-zero correlator. Okay. And the hint, okay, is that you have to use plumbing fixture to build these genus G correlation functions, and you use the fact that the host number of phi r c, host number of phi r c is 6 minus host number of phi r. Okay, that follows from this relation that phi r c phi s equal to delta RS. Okay, so if phi RC and phi R are the same, then there is a non-zero inner product, but that requires that the sum of the host numbers must add up to 6. This is on the sphere, of course. Okay. And these together with plumbing fixture can be used to prove this general result. Okay, so these I'll leave as an exercise. Okay, so this tells us that in principle we can define genus G correlation functions for conformal field theory. Okay. But now let's ask the question, okay, that you are interested in string theory. Okay. So why are you interested in correlation function of higher genus surfaces? In correlation function of higher genus surfaces. And the answer is the following. So I'll give the first the intuitive answer, okay, and the intuitive understanding of this, and then we'll make it more precise. Okay. So the answer is that a G loop amplitude in string theory is expressed in terms of CFT correlators on genus G surface. Okay. And hopefully by the end of today, we'll see the explicit expression for this G loop amplitude. Okay. But first, let me just give an intuitive understanding. Okay, and this will be based on some example. So example 1. Take a one loop 4-point amplitude in QFT. Okay. So what kind of Feynman diagram? So let's draw a Feynman diagram. Okay. The Feynman diagram is of this kind. Okay, this is one particular example. Okay. Now these crosses I'll explain. Okay. So what I'm computing here is what we call amputated Feynman diagram, amputated amplitude. Okay. Where I've removed the external legs. Okay, because that's what enters the expression for the S matrix. Okay. So I remove the external legs, and where the external leg first connects to the Feynman diagram, I just represent by a cross. So now let's see intuitively what it will become in string theory. Okay. So essentially in string theory, we expect that all these internal lines will fatten into cylinders. Okay, if it's closed string, because a string worldsheet is a cylinder instead of being a line. Okay, so these will fatten into closed strings. Okay. So it will become, so we fatten internal lines. Okay, and let's see what it becomes. So it becomes a diagram like this. My drawing is not going to be very good, but I'll at least try to explain. Okay, so you think of this as a pipe. It's not. Okay, so these you should think of as pipes. Okay, so it's like a donut. Okay, and you have these 4 points where the external lines join. Okay. So you see that this is already a genus 1. Okay, that torus 4-point. It looks like a 4-point correlation function on a torus. Okay. So this looks like 4-point function on torus. Okay, but we are going to eventually translate this into a precise expression. Okay, but right now I'm just giving the intuition. Okay, that's why we expect the one loop amplitude to be related to genus 1 correlation function. Okay, I'm going to describe one more example. It's a 2-loop 3-point function. So let me draw a diagram. This is a possible Feynman diagram, right? Okay. Again, the convention is that this is where the external legs are attaching. Okay, which I'm not going to draw. Okay. And now we fatten it. So if we fatten it, it becomes something like this. Okay, again, each of these one should think of really as pipes. And then you have the usual 3 other points where the external lines attach to the surface. Okay. So this now looks like a genus 2 3-point function. So this is the reason we expect that a G loop amplitude in string theory should be given in terms of some genus G correlation function. Okay. But now we have to ask, what is a precise dictionary? Okay. So we need to know what is a precise dictionary. So there are 2 sides to this dictionary. So let me explain what these 2 sides are. So the first one is what is computed. Normally we think of the CFT as giving the string S matrix, but as I'll discuss in detail, okay, what it gives directly is not the string S matrix. You have to do a little more work to extract the string S matrix. Okay. But whatever it gives can be used to extract the S matrix. Okay, but before we can say how to extract the S matrix, we need to know what exactly is being computed. Okay, only then you will know how to relate to S matrix. Okay. So this I'm going to state in the QFT language. Okay, that if you are doing a QFT, what does it correspond to? What is the quantity that you are computing? Okay. And then the second part is how is it computed? Computed using CFT correlators. Okay. So first, let me try to answer the first question. Okay, what is computed? So what is naturally computed in terms of CFT correlators is the following. Okay. What we compute is an off-shell Green's function with tree level. Let me state this more clearly. with external tree-level propagators removed. So this is not quite the amputated amplitude that you are familiar with in QFT. Okay, so that in terms of Feynman diagrams, I'll explain what it is, what is being computed. Okay, so suppose let's think in terms of QFT. Okay, even though we are doing string theory, but we would want to know what in QFT would it correspond. Okay. So imagine that you have a QFT Feynman diagram like this. Then what we will compute? So this is we think of this as a Green's function, okay, not necessarily on cell external states. And what we will compute in string theory is the quantity where you just remove this 1 over k square plus m square factors from the external lines. Okay, so this is like amputated Green's function. But suppose we also have a diagram like this. Okay, let's take a diagram like this. Then the quantity that I will compute, okay, will correspond to removing the tree-level external propagators, which means these, and these. But this part of the diagram will be included. Okay, so it's not quite the amputated Green's function that you are familiar with in quantum field theory. And so on. But given this, okay, suppose we know how to compute this, okay, then we can construct the full Green's functions, because of course the tree-level propagators we know what they are. Right? So you can always multiply the what we compute by this 1 over k square plus m square factors. Okay. So this can be used to get the full Green's function. And then we can apply LSZ to get the S matrix. So that's the fully systematic procedure for extracting S matrix of string theory from conformal field theory. I'll tell you in part B, I'll tell you how to use conformal field theory to calculate these objects. Are there questions? Is this clear? What I'm saying here? Okay. Now, if we are working with 3 amplitudes, then you can easily convince yourself that what we are describing here is precisely amputated Green's function. Right? Because in 3 amplitude, of course, you don't have diagrams like this. And there, if you take the external states to be on shell, you'll get S matrix. Right? So normally when you say that the CFT correlation functions can be used to calculate the string S matrix, okay, we specifically refer to tree level, and there it's true that CFT correlators directly give the S matrix. Sometimes for loop amplitudes, also the CFT correlators give S matrix. And that happens provided diagrams like these are automatically 0. And in some supersymmetric theories, it does happen. With theories with a lot of supersymmetry, one can argue that the 2-point functions vanish. Okay, so there is no self-energy diagram that is involved. Okay. And there again, okay, removing these external tree-level propagators give you the amputated Green's function. And if you put the external states on shell, you'll get the S matrix. Okay. So when we say that the CFT can compute the S matrix directly, okay, it's only in these special cases. Okay, either at tree level or with theories with sufficient amount of supersymmetry, okay, so that the external these diagrams are absent, okay, from the beginning. Okay. But in general, okay, if you want to compute S matrix from CFT correlation functions, you have to go via this route. So the sum of diagrams like these, okay, I'll call the amplitude. Okay, even though it's not an usual terminology. Okay. So this will be called amplitude. Okay, so when I say that we'll be writing down the expression for the amplitude, okay, this is what it will be. Okay. And then you have to take that amplitude, okay, with offset external states, okay, and then convert this into S matrix using the standard LSC procedure. Okay, now let me describe what you mean by off-shell string state. Definition of off-shell string state. And this will be as follows. So this is will be by definition a state V in the CFT satisfying B0 minus on B equal to 0 and L0 minus on B equal to 0, okay, but not necessarily QB on B equal to 0. Okay. So this one will regard as the on-shell condition. So when you say that you are going to give the prescription for computing an off-shell amplitude with some external string states, we'll be basically considering external states beyond V2 up to Vn, if it's an n-point amplitude, each of which satisfies this condition, these two conditions. Okay, and some of them may satisfy this condition, but it's not necessary, because if it does satisfy this condition, we'll call them on-shell external states. Okay. So now we want to ask how to compute, what to compute, or how to compute the amplitude as a function of the V1 to Vn. Okay. And this will be the rest of today's lecture. Okay. Exactly what is the formula for this A. So to do this, we will begin with a general description of Riemann surface. So the claim, which I'm going to illustrate in the next page, okay, by drawing diagrams, is that this can be regarded as a union of n disks one around each puncture and 2g minus 2 plus n spheres each with 3 holes, and they will be joined at along 3g minus 3 plus 2n circles. So we'll denote the disks by dA. Okay, with A equal to 1 to N. Spheres by SI, I equal to 1 to 2G minus 2 plus N. And circles by CS with S equal to 1 to 3G minus 3 plus 2N. Okay. And these circles are essentially the intersection of two spheres or a sphere with a disk. Okay. So these can be either SI intersection SJ or SI intersection D. Okay. This seems somewhat abstract, but I'm going to draw an example of a figure in the next page where everything should become clear. Okay, so the example that I'll be considering is G equal to 2, N equal to 2. So let's draw a genus 2 surface. And let's suppose that we have two punctures, one here, one there. So now let's start drawing the circles, okay, which will divide the disks and spheres. So around each puncture there is a disk. So let me draw those disks. Okay. So in interior of this is what I'm calling D1. Interior of this is what I'm going to call D2. Then we have to divide this into spheres with 3 holes. So let's draw some holes, some circles. So let's label. So D1, D2 have already labeled. So this is the first sphere. Okay, you can see that this has a topology of a sphere with one hole here, one hole here, one hole there. This is the second, this is third, and this is the fourth sphere. Now, how many circles are there? Here is C1, C2, C3, C4, C5, C6, and C7. Okay. So let's now see if the counting matches. Okay, so what I had claimed earlier is that the number of spheres, number of disks for the number of punctures, that's true. The number of spheres was 2G minus 2 plus N. Okay. So how much should that be? So G equal to 2. Okay. So that's 4 minus 2 is 2 plus 2, that's 4. And indeed there are 4 spheres, 1, 2, 3, 4. And number of circles is 3G minus 3 plus 2N. So that's 6 minus 3 is 3 and 2N is 4, so that's 7. And indeed we can see there are 7 circles, 1, 2, 3, 4, 5, 6, 7. So this is just an example, but this is generally true. Okay, you can convince yourself that any genus G Riemann surface with n punctures has this feature, that it can be divided into disks, spheres, disks and spheres, okay, and separated by these many circles. Now on a circle, okay, maybe I should, Okay, are there questions on this? Is it clear? Now let's fix some orientation on each circle. Okay, this is arbitrary. So once you have fixed the orientation, we call sigma s the coordinate on the left of the circle. So sigma s will correspond to, oh, I should have, sorry, maybe let me go back a little bit. Okay. So we introduce coordinate system. Complex coordinate system. WS, sorry, WA on the disk with WA equal to 0 being the function. Okay, that's the way we'll choose our coordinate system. Otherwise, we leave it arbitrary. Okay. And Zi on Si. Okay, on each sphere you can choose complex coordinate Zi. Okay, so you call that Zi. Okay. Some arbitrary coordinates. Now we go back to this. We call sigma s is the coordinate on the left of CS. Okay. So this could be either Zi or WA. Depending on what is there on the left of CS. Okay. Left is well defined because I have already fixed some orientation on CS. Okay. The final result doesn't depend on the orientation. Okay. So sigma s is the coordinate on the left of CS, okay, which could be either Zi or WA, and tau s could be the coordinate on the right of CS, which again could be Zi or WA. And in general, specifying the Riemann surface means that specifying the relationship between sigma s and tau s. So tau s is equal to Fs sigma s. Okay, this is what we call the transition function. Okay, as you go from one coordinate patch to the next coordinate patch. So tau s is some function of sigma s. Okay. And specifying all the Fs's basically specifies the Riemann surface combination. But of course, there is a lot of redundancy, okay, which I'm going to describe in the next slide. So consider the equivalence class. Consider, okay, let me write it this way. Okay. So if you take a function, a set of functions, Fs of tau s, one for each circle, okay, take the collection of these functions. Okay. This is considered equivalent to, say, Fs tilde of tau s, a different set of functions, if they can be related by coordinate transformation of the form zi goes to some arbitrary function of zi, okay, which should be 1 to 1 on the si, okay, outside it doesn't matter, and which means there can be singularities inside the holes, okay, because the holes are not part of si, and wa going to some h tilde a of wa, okay. But we impose the condition that h tilde of 0 is 0, okay, which means that these coordinates, the transformations, do not change the location of the puncture. Okay, the puncture is kept at the origin in the new W coordinate system. So this defines an equivalence class. Okay, so the space of equivalence classes is finite dimensional. Okay, precisely, it's 6g minus 6 plus 2n dimensional. This is real dimension and known as the moduli space of genus G. The Riemann surface with n punctures. Okay, so inequivalent Riemann surfaces with punctures are related by those which cannot be related, for which these transition functions cannot be related to each other by coordinate transformations of this kind. Okay. If this condition was not there, then the dimension will be reduced further by 2n. Okay, and there, in fact, we have the that will be the moduli space of genus G Riemann surfaces without punctures, because the location of the information about the punctures essentially comes to this information that we only allowed coordinate transformations, okay, that do not move the punctures. Okay, so that restricts the set of allowed coordinate transformations and hence increases the dimension of the moduli space. So finally, the amplitude, okay, will be expressed as an integral over this space. Okay, but we have to understand what the integrand is. Okay, but ultimately it will be expressed as an integral over this space. So let me give this space a name. Okay, so we'll call this moduli space as M Gn. Okay, genus G Riemann surface with n punctures. Now we are going to introduce another space, okay, which is infinite dimensional. So introduce another space. Pgn. Okay. So this is equivalence classes of these fs, these functions, under coordinate transformation zeta equals to hi of zi. Okay. So you allow arbitrary coordinate transformation, okay, on the spheres, but you don't allow the coordinate transformation on the disks. So this is what we call PGN. Okay. So what PGN contains? So physically, PGN contains information I made a mistake. Okay, I have to correct this. Okay, there is something I have to add here. And WA goes to e to the I alpha A times WA, where alpha A are arbitrary constants. Okay. So we define these equivalence classes. So we don't allow coordinate transformation on WA, okay, except phase rotation. Okay, you have to, if two sets of FSS are related by phase rotation of WA, we declare them to be equivalent. Okay, this is necessary. Okay. So now let me say physically what this is. So physically, PGN contains information about MGN, okay, the point in the moduli space, and choice of local coordinate at the puncture. Okay. So in other words, okay, if you make an arbitrary reparameterization of W, right? So WA goes to some function of WA, okay, then that is changing the local coordinate system around the puncture. Okay. And that is considered as a different point in PGN, because PGN, a point in PGN has a fixed set of choice of local coordinate system. Okay, a different choice in point in PGN will have different choice of local coordinate system. Okay, so if you have the same moduli, okay, but different choice of local coordinate systems, okay, so if we think in terms of the example on the sphere, okay, imagine that on the sphere you have fixed the locations of the punctures. Okay, so that fixes where in the moduli space you are in. Okay, but you still have a choice of changing the local coordinate system around each puncture. Okay, and that information is in PGN. Okay. So pictorially, one can represent PGN as a fiber bundle. Okay. So PGN can be regarded as a fiber bundle with base MGN, okay, and fiber containing choice of local coordinates. Okay, so pictorially, if you draw, so this is the picture of PGN. Okay. So PGN is the whole total space. Okay, MGN is this base space. Okay, and if you go vertically up this direction, okay, this means that you have kept the point in the moduli space fixed. Okay, a fixed genus Riemann surface with a fixed set of punctures. Okay, but you are changing the choice of local coordinate system at different punctures. Okay, so this is the direction in which the local coordinates change. Okay. So PGN is infinite dimensional. Intuitively, it should be clear, is infinite dimensional. Since it has information about n independent functions. That is choice of local coordinates. Okay, but up to phase. If you just change the phase of the local coordinate, it's considered as the same point in PGN. If there are questions, please ask at this stage. Okay, so let me introduce some formal notation. Tm, okay, which I'll also denote as a vector T, are the coordinates on PGN. Okay, there are of course infinite number of them. Infinite number of coordinates. Okay, fortunately, when you actually do actual computation, you don't have to deal with this infinite number of coordinates. But right now, let's introduce a full infinite set of coordinates. Okay, so this means that given the point T, given T, we have a given, we are given okay, I'm now going to put the T in the argument of Fs because changing T will change the function Fs. Okay, that's what one means, right? Because different choice of functions Fs correspond to different points in PGN. Okay, so that's why I have put the T inside Fs. Okay. Given set of functions Fs, but of course Fs is not unique. Okay, it's not unique because it's not unique since it can be changed by Zi parameterization or Wa goes T to the I alpha times Wa. Okay. But just pick some representative. Okay, pick some representative Fs. Okay, so that's our I'll write Fs of tau S and T. So let me remind you what Fs was. Fs was relating the coordinate, the complex coordinate on the left of CS to the complex coordinate on the right of CS, that is T tau S. Okay, so far it's only properties of Riemann surface. Okay, we have not talked about the CFT anywhere. Okay. Now we are going to bring in the CFT. So we are going to define a CFT operator. Okay. Now operator I put in quotes. Okay. Because as we discussed that CFT on a hard genus Riemann surface doesn't really have a full Hilbert space interpretation. Okay. But I call it operator only in the sense that we know how to calculate its correlation functions. Okay, so whenever I am talking about CFT operator, you should think of this as being eventually put inside a correlation function. So the CFT operator that we will define is this Bm, capital Bm, which is sum over S. S runs over all the CSS, right? 3G minus 3 plus 2n objects. So let me write 1, 2, 3G minus 3 plus 2n. Okay. So when I write B sigma s, this is B evaluated in the sigma s coordinate system. That's the notation we have been using all through, right? So the argument also tells us what coordinate system we are using to insert B. Okay. This derivative, okay, is taken at fixed hours. Okay, we take the derivative of fx with respect to Tm at fixed hours. So that's the definition of the operator B, Pm. Okay, I hope it's clear. Now let's suppose that we have a set of off-cell string states.
Sorry, I have a question. Why is that operator a CFD operator?
Because there is a B. B is part of CFD, right?
Oh, right. Okay.
Yeah, so that's the reason why it's a CFD operator. So it will make sense only inside a correlation function. Okay, and we'll soon put this B inside a correlation function. Okay, we are going to define a P form for arbitrary P. P is an arbitrary integer, okay, on PGN, and this will depend on the some of the fixed set of external off-cell states, which I'll denote by P on to Pn. Okay. And here is the definition. I use a different color. So omega P Gn P on to Vn is these B's are the ones I defined just earlier. P on to Vn sigma Gn. Okay. So I have to explain what the sigma Gn is. So sigma Gn is a genus G Riemann surface with n punctures. N punctures. And given choice of local coordinates at punctures, determine by the point at PGN. Okay. So let me explain what this means. Okay. So you see, this is supposed to be a form on PGN. Okay. So it's a form. It's clear, right? Because you have the wedge product of DTM1 to DTMP. So this is a P form. Okay. But this a form on PGN, of course, will depend on the particular point at which we are computing the form. Okay. So where does that information go in? Okay, the point at which you are computing the form, that's information is in sigma gn. Okay, so sigma gn is a Riemann surface, okay, corresponding to a particular moduli. That information is certainly there in PGN, but it also comes with its own choice of local coordinate system at the punctures, because PGN contains that information as well. Okay, as you go vertically up in PGN, you will change the local coordinate system. Okay. And these VIs, the V1 to Vn, the vertex operator that you have introduced here, okay, these are inserted using the local coordinate system. Okay, so this uses, this one is at W1 equal to 0. Okay. Similarly, this one is at Wn equal to 0, okay, using the Wn coordinate system. Okay. So in other words, if you fix the point in the moduli space and if you change the local coordinates, that means if you go up the fiber along the fiber direction, okay, this will still change, okay, for an off-shell state, because the local coordinate system changes. So this is the abstract definition of a form in PGN. Is this clear, the definition?
Yes, but excuse me, can we have an intuition what this form is doing?
Well, we'll do an example of a 4-point function. Okay, we'll sphere 4-point function using this form. Okay, and there it will become clear. This will basically be the form that you have to integrate over the moduli space to compute string amplitudes.
All right, thank you.
Okay. Now let me just state a few nice properties, and later on we will discuss other properties. Okay. So that first is that this description is manifestly invariant under change of coordinate in PGN. Namely, if you take Ti to some function of T, the form remains manifestly invariant, and you can see this easily because you see when you change T to some function of T, these of course it changes by f prime of T dt. Okay. But if you look at remember the definition of B, the definition of B has this del T. Okay. So the combination that appears here is really the del Fs del Tm times dTm, and that is independent of a deparameterization of T. Okay, manifestly del Fs del Tm times dTm is manifestly invariant under deparameterization of T. So it doesn't really matter what kind of coordinate system you choose. The other useful information is that if we want to pull back this form omega g and p on some p-dimensional subspace of PGN. Because after all, a P form is supposed to be integrated over a p-dimensional subspace, right? So eventually you'll be interested in pulling it back on some p-dimensional subspace. So if you want to pull it back on some p-dimensional subspace, okay, with intrinsic coordinates, you want to UP, then the result is obtained simply by replacing Tm by UP by P-wise. Okay, in other words, if you suppose you are not interested in computing the form everywhere, okay, but just its pullback on some p-dimensional subspace, okay, you label this p-dimensional subspace by some set of coordinates u1 to up. Okay, then for this b, you define the corresponding component using u. Okay, so you take the derivative with respect to uk here, del uk and del uk, okay, and here you contract with duk. Okay, so here you will have some du1 to the up, okay, and that's what will be the pullback, right? This again you can convince yourself easily, okay, by using this structure that the actual combination that appears, okay, is this derivative with respect to tm times dtm. Okay, so you can easily, by chain rule, you can easily convert this into derivative with respect to u times um. Okay, if you are on a p-dimensional subspace. Okay, so we'll be eventually computing these pullbacks. Okay, that's what is necessary, will be necessary. And for that, this information is useful.
What does the p signify, this integer p?
Okay, right now the integer p can be anything. Okay, but ultimately for actual physical string amplitudes, okay, we'll be interested in p equal to 6g minus 6 plus 2n. Okay, but defining this for general p is useful, as we will see, because that way we can go up and down. We'll see some applications, okay, of why defined p's are useful. Okay. But string amplitudes will be expressed in terms of a p form where p is 6g minus 6 plus 2n, because that's the dimension of the moduli space. Is this clear?
Yes, thank you.
Okay, so now we are ready to define the amplitude, off-cell amplitude. So definition of off-cell amplitude. So the step one is to choose a section SGN of PGN. Okay, so section means that you choose some section. Okay, so these are our PGN. This is PGN, and here is MGN. Okay, so the section has the same dimensionality as MGN. Okay, that's 6g minus 6 plus 2n. Now the definition of A. So A V1 to Vn is integral SGN. Maybe I should write down the coupling constant first. Okay, so there is a string coupling constant GS that I'm going to introduce. Okay, arbitrary dimensionless constant GS to the power 2g minus 2 plus n integral SGN omega g n okay, so instead of p form, with general p form, we take the 6g minus 6 plus 2n form and then we integrate over this section. That's the definition of the amplitude. So from this amplitude, as I have already said, tree-level S matrix is directly the amplitude. In fact, more precisely, it's I times A. Okay, I is the standard I that comes from the Euclidean to Lorentzian rotation. Okay, so this that's the convention I have chosen. So you have to multiply by this I. Okay. If you want to compute loop level S matrix, in general, it requires LSZ. Okay. But as I said, in theory with high amount of supersymmetry, certainly not in bosonic string theory that we are discussing, but in theory with high amount of supersymmetry, where these two-point function, the self-energy corrections vanish. Okay, there again, this directly gives the amplitude, the S matrix. IA gives the S matrix. Okay. But in general, you have to go through this LSD procedure to extract the S matrix from this expression. Okay, now we are not going to derive this formula. Okay, we will not derive this formula. Okay, you can, in a sense, you can take that as a definition of string theory, right? What string amplitudes are. Okay, even though there is some kind of derivation that one can give, starting from the original Polyakov path integral. But we'll test various, we'll check various consistency conditions. Okay. To do that, we need a crucial identity that this omega satisfies. And this, in fact, is derived using CFT properties. Okay, it doesn't require anything else. But let me write down the identity. Okay. The identity goes as follows. Okay. You remember -1 to the V1 basically is 1 if V1 is Grassmann even, and it's -1 if V1 is Grassmann odd. Okay, which in turn depends on the ghost number of. Plus it goes all the way up to omega p gn V1 up to Vn -1 QB Vn. Okay, and this has to be multiplied by -1 to the V1 -1 to the V2 up to -1 to the Vn -1. Okay, because QB is Grassmann odd, so as it goes past each, it picks up this -1 to the V factors. So this is given by -1 to the P d omega P -1 Okay. Now at least you see the utility of using arbitrary P, because if you had only defined omega for 6g minus 6 plus 2n, then this relation will not make sense. Okay, so that's why it's useful to work with at least introduce omega for arbitrary P. Okay, even though eventually we are interested in integrating over a 6g minus 6 plus 2n dimensional subspace. Okay. Now here one notation I should say this: what is QB V1? So QB V1, QB V of ZZ bar. Okay, so this is a local operator evaluated at ZZ, but this by definition is integral over W. Sorry, integral. So this means it's integral. The integration contour is around Z. Okay, so if this is Z, basically we integrate the contour around encircling Z. Okay, that's the definition of QB. Okay. And you can easily convince yourself that if you take this, if you define QBV this way, then QBV on 0 is nothing but QB on the state V. Okay, so this is the identity. Okay, as I said, it basically is derived using CFT properties. But let me just say what CFT property one uses. I have to go to the new slide, but I'll come back to the. So basically, one has to use the fact that QB of B is T. Okay, this is an identity, and then QB with B bar, Z bar is T bar Z bar. So this is the total energy momentum tensor, Tx plus TBC. Okay, this I leave as an exercise. Okay, given the definition of QB, you can prove this. Okay, so the way one proves this is that you take this sum of QBs, right, which are these QB contours around the V's. You try to deform it on the Riemann surface. Okay. In that process, the definition of omega, okay, if you recall, has these B's inserted. Okay. Has this B's inserted. So you pick up commutator of QB with these B's. Okay. And that expresses the small b in terms of capital T. Okay. And finally, you have to use the fact that integral epsilon z tz dz, this generates z goes to z plus epsilon z. Okay. So these transformations, okay, z goes to z plus epsilon z, essentially moves you in the moduli space, right? That's why you see on the right hand side there is d. Okay. So d is d in PGN, right? That means it's actually moving in either in the moduli space or it's changing the local coordinates. Okay. And it's doing this, okay, by using the fact that this generates a change in coordinate system. Okay. Anyway, this is just a sketch. Okay. But what all I want to emphasize is that this identity, okay, one can derive, okay, very explicitly just using CFT properties. Okay, using various identities in CFT. The other point I want to emphasize is that this integral, okay, the normalization, okay, I have introduced this integral earlier also, okay, but let me just say the normalization is that this integral is defined such that integral dz over z is 1 and integral dz bar over z bar is 1. Okay, that's the normalization, which means that these includes 1 over 2 pi I factor. Okay. So in the rest of today's lecture, I'll now show how we can use this identity to make some consistency checks. Are there questions?
Can you hear me?
Yes, I can hear you.
I just have a question about the definition of the off-shell amplitude. Is it independent of the choice of the section?
Does it depend choice of the section? Yes, indeed, it does. I'm going to that's what I'm going to discuss next.
Okay. Okay, thank you.
Yeah. So how does section dependence comes in? Okay, so let's look at the consequences. So first we study the dependence on the section. Okay, so let's draw this PGN. And let's suppose that we have made two different choices of the section, SGN and S prime GN. And we want to compute the difference. Okay, that if you evaluate the amplitude using SGN or S prime GN, what is the difference? Okay. So for this, we need to calculate integral over SGN of omega GN minus integral over S prime GN So this I can write. You see, given these two sections, I can find a n plus 1, sorry, 6g minus 6 plus 2n plus 1 dimensional subspace that fills the gap. Okay. This subspace is not unique in higher dimension. Here it looks like it's unique, but in general, if you have, say, in 3 dimension, 2 different curves, you can fill the space between the 2 different curves in many different ways. Okay. So, but doesn't matter. Pick one way to fill this gap. Okay, let's call this RGN. So this then I can write as the integral over RGN of T omega GN 6g minus 6 plus 2n P1 to Vn. Okay. And then by using this identity, I see that this is given by integral RGN. I think there is a minus sign here, okay, because of this minus 1 to the p. Okay. So omega GN 6g minus 6 plus 2n plus 1 QB B1 B2 to Bn plus omega GN here you have V1 QB V2 V3 to Bn plus etc. There is a minus 1 to the P1. And now we see that this, okay, and I should also say that plus possibly boundary terms. Okay, I'll mention it later. So this is 0 if QB VI equal to 0 for every I. So if the external states are on shell, then the result doesn't depend on the choice of section. Now, on shell here doesn't necessarily mean that it has to be of the form CC bar times dimension 1 on primary. Okay. It can be that plus any QB on something. Okay. As long as QB VI is at 0, okay, this difference vanishes. So the on shell amplitudes do not depend on the choice of section. Is this clear? Are there questions? Now I should just say here that this, I mean, the way I have drawn this, right? I drew this RGN, but in general, that can also be contribution from the boundaries of MGN. Okay. So this argument has to be supplemented. So this has to be supplemented by separate analysis of contribution from the boundary of MGN. Okay, this is the boundary of MGN because it goes on, but if the MGN has boundaries, okay, boundaries of MGN are in fact precisely the degeneration points, okay, where the Riemann surface splits up into either two Riemann surfaces or some handle degenerates. So those have to be analyzed separately, and one has to make sure that those boundary terms do not perturb. Okay. But this can be done in a generic case. Okay, so this is the proof that on-cell amplitudes do not depend on the section. Off-cell amplitudes do, but eventually, after you do LSG and you extract the on-cell amplitude, again you can show that section dependence goes away. The second point that I want to discuss is the following, okay, and that's the decoupling of the unphysical states. So let's consider the following quantity. Okay, suppose the first entry is QB lambda, okay, which you had called pure gauge state, and then the others are V2, V3 up to Vn, okay, with QB Vi equal to 0 for I equal to 2 to n. Okay, so what you are looking at is an amplitude where the first state is pure gauge, okay, the rest of the states are physical. So this is, I can now write, this is the integral omega integral SGN omega GN but I can always add to this lambda QBV2 up to Vn minus 1 to the lambda plus the whole bunch of other terms, because QBV2 is 0 anyway, right? Because this is 0 anyway. So you are just adding zeros. But once you have added these zeros, okay, we can apply the identity that we had derived. Okay. And this can now be written as integral over SGN B omega GN. Again, now you can see why we introduce omega for generic P, okay, because now this argument will become 6G minus 6 plus 2n minus 1. And this is again 0 up to contributions from the boundary of the moduli space, which have to be analyzed separately. Okay, this to be analyzed separately. And generically, these all vanish. So this shows that the pure gauge states decouple. And this, in a sense, is the proof of general coordinate invariance. And other gauge invariances like the two-form gauge invariance. in the interacting theory. Because it's not linearized general coordinate invariance anymore. It's the full general coordinate invariance in the nonlinear theory. Are there questions?
Ashok, I think it would be useful if you could give some examples of boundary of moduli space, because probably some students are not so familiar with this concept.
Yeah, okay. I mean, in fact, that will be, a whole, at least one lecture of discussion of the boundary of the moduli space. Okay, but maybe I can just say what one means by the boundary of the moduli space. It's basically this. You remember that if you take two spheres, okay, let's take simple 2, 3 punctured spheres, and identify. In fact, this will again come in the example that I was going to show. Okay. You identify W prime equal to minus Q. Okay. That gives a 4 punctured sphere. Okay. But the Q goes to 0 limit is somewhat singular. Okay. Because you see, you are identifying these. Okay. And this corresponds to mod W equal to mod Q to the half. Okay. And this corresponds to mod W prime equal to mod Q to the half. Okay. So Q goes to 0 limit. Is somewhat singular because this is basically saying that the two spheres are joining, but they're joining by a very, very narrow neck. So this is a boundary of the moduli space. Boundary in this case of M04. And we'll work out the precise map next time. In fact, I think we have already seen part of this before. Okay. This we can also, there's a interpretation of this. Okay. That if you take a plane with 4 punctures, okay, the boundary corresponds to when the two of the punctures come close. Okay. So if instead of having well separated punctures, if you have a picture like okay, if these 2 punctures come close, okay, this you can show is precisely, this is precisely the Q goes to 0 limit of the previous diagram. Okay. Next time we will be applying this whole technology to sphere 4-point function, where I think all of these should become clear. Are there questions? Okay, so let me then say what we are going to do next time, okay, but not say very much more. So this whole technology that we described, okay, we are now going to apply on a very simple example, okay, where you don't need so much technology, but nevertheless, it's good to see how it works in that simple example. Okay. So we'll apply this to sphere 4-point function. Okay, which is M04. G equal to 0, number of punctures 4. Okay. So this has 6G minus 6 plus 2n, 6G minus 6 plus 2n. N is 4, G is 0. So this is 2-dimensional moduli space. Okay. And here we will be computing on-cell amplitudes. So you don't worry about the local coordinates very much. Okay, nevertheless, you'll have to introduce the local coordinates. And we'll see how this goes, right? So the way we'll proceed is that we'll take the sphere with 4 punctures. We'll choose the 4 punctures over here. We'll draw the circles. Okay. So if we call this C1, C2, C3, C4, and C5. Okay. And if we call this D1, D2, etc., D3, D4. Okay. And we call this the first sphere. Okay, this is our S1 and this is our S2. Then you see that we have the relation. Let me write down the relation and then I'll stop. So on C1, we have the relation Z1 equal to F1 of W1, right? Because the coordinate, okay, let me choose the contour, the rotation this way, the contour orientation this way. So Z1 equal to F1 W1 because Z1 is to the left, right? This coordinate system is Z1, inside is W1. So Z1 equal to F1 W1. On C2, Z1 equal to F1, F2 W2. So C3 will have Z2 equal to F3 of W3. C4 will have Z4 equal to F4, sorry, Z2 equal to F4 of W4. Okay. And finally on C5, we have, let's put the Z1 on the left. So it's like this, Z1 equal to F5 of Z2. Okay. And you have to introduce basically 2 parameters because you are trying to draw a 2-dimensional section, right? We'll have to introduce 2 parameters here. Okay, we can put it in any way we like. Okay. But we'll see that the easiest to do this is that I'll choose F5 to be minus Q by Z2. Okay. And we'll choose these to be independent of Q. Otherwise, it doesn't, we'll leave this completely arbitrary. Yeah, at least for now. And then we are basically going to apply this whole machinery that we develop to write down the amplitude for this 4-point function. Okay. And we'll see what we get. Okay, so I think I'll stop here. Okay. And we'll continue next time on Monday.
Okay, so if there are some quick questions, otherwise we can. So today there is one more discussion session, so we can also ask questions in that occasion. Okay, so otherwise, hi, Ashoke, thanks for the lecture.
Okay, thank you.